Okay, here we go. Hello and welcome to the session Trash Talk, exploring the memory management system of the JVM, which is part of the No Fluff Just Stuff webinar tour. All right. So my name is Gerrit Grunwald. I'm working for Azul as a senior developer advocate, and today I will tell you a little bit about the JVM memory management and especially about garbage collection. So just upfront, this is not a garbage collection deep dive because it's more like an overview and give you some ideas about the different garbage collection principles and garbage collectors that we have in OpenJDK. So memory management in the JVM. It's automatic, right? So why care? Well, it has an impact on application performance and application responsiveness, and also on the resource management. And that three things are all very important parts, and you are involved on your daily work with this kind of stuff. So that means you should really have an idea about memory management in general, right? At least how it works. So let's see what we have to tell you here. So if we take a look at how the JVM is structured memory-wise, then we have threads. And for each thread, we have a so-called stack frame. And the stack frame, as you can see on this diagram here, contains primitives and references to objects. And it grows and shrinks dynamically. So it's thread safe because it's local access only. Then the next part that we have is the so-called heap. And in this heap, the actual objects are placed, right? So this is the memory area where we have objects, the virtual memory. And this is not thread safe, and we need to do garbage collection here. So we need to take care about the memory management in this part of the JVM memory. And then we have the so-called meter space, which contains class metadata, constant pool, a method bytecode. So this is not really fixed size, so it's growing dynamically. And this is, in principle, contains all the information that you need or that the JVM needs to work with classes. But we will only focus on the two left parts in this diagram. So if we take a look at this code, which is a very basic example, then you see we have some records here, some persons, like we have 4 persons, and then we have a list that contains references to all of these persons. And if we print out, for example, P1, then we see my name, which is Gerrit. Okay, that's fine. So if we now take a look at how this is structured in the JVM, then we see we have a stack area for the main thread. And there's a frame. In this frame, we have the references for all of these objects and also for the list. And then we have the heap. And in the heap, we have the actual objects, right? That means the 4 objects for the persons and also for the list. And these references point from the stack into the heap to these objects. And you see the list also points to each object because it contains references to this object. So that's pretty simple. If you now, for example, see all these objects, you can reach from this stack frame into the heap, right? They're all reachable. And that means they are live. So because everything that you can reach is live. If you can't reach it anymore, it's dead, right? So then it's just lying around in the heap, taking space, and you can't really do anything. So if we now set the P1 to null, then you see the reference is gone to the object, but we still can get the object via the list object because the list contains a reference to the P1 on the heap. So you can see on the left side, if I print out persons get 0, which is the first object here, the P1, then you will see it will print out the name, even if the object is already null. So if I now remove the list reference by just setting the list to null, then we lose track of these objects. And then the only objects that are still reachable are the P2, P3, and P4. The rest is more or less garbage. It's lying around in memory in the heap, and it needs to be cleaned up somehow. So how can we get rid of this stuff? Well, this is garbage collection in principle, right? So someone has to clean it up because otherwise we fill up memory, in this case, the virtual memory area, the heap, and then at some point we run out of heap memory. So we need to clean it. And therefore, there's garbage collection. What is it? It's one form of automatic memory management. There's also automatic reference counting and other stuff. For example, Swift uses automatic reference counting, and there's no better or worse. They both have their advantages and disadvantages. It's just a different principle. It identifies and reclaims no longer used memory, ensures efficient memory utilization, and frees users from managing the memory manually. This is more or less the most important part here. And because it's not just one step, right? It's not just clean the memory. It's separated in so-called phases. And if we take a look, and this is true for all precise collectors, then first of all, we have the tracing phase, right? And the tracing phase identifies live objects on the heap. Remember the stuff where we have the reference, objects that we can reach, right? Tracing finds these objects on the heap. And then we have freeing. It means we need a process that cleans up the rest of the heap, right? Finding the dead objects and then removing them, free the space. That's freeing. And then we have compaction. Because you can imagine if we just fill up space and then we remove parts of it, then it will be fragmented, right? So then we need to clean it up and compact memory. So that means we periodically relocate live objects. We move them around in the heap and compact them to make more space available that is in one piece, right? That's the idea. So these are the three phases where most of the garbage collectors work in the JVM. And then I have to tell you something about stopping the world, because these days people don't really know, not everybody knows about it anymore. I was a little bit surprised, but years back, that was a big topic, right? Stop the world. Oh, we have this stop the world garbage collection process and it's terrible. But what does it really mean? So if we take a look at the JVM, then we have different threads that we have available for application. And these application threads are running over time and do their job. And then if we would like to do a garbage collection, then we send a so-called signal, right? So we have the running application threads, as you can see here. Then we send the save point signal, that's the name of it. And that means all the threads have now to stop their work. And until everything is stopped, then we reach the JVM save point. That means no application thread is running anymore. And that means because no application thread is running, there's no access to memory anymore at that moment, right? No allocation, nothing. So, and that gives the JVM the freedom to use threads for garbage collection, clean up everything. And when this is done, we just resume the application threads and the application can continue running. So, you know, can I imagine that the time that we spent in the garbage collection, nothing happens. The application will completely stop. And in the past, if you have a big application with a big heap, then it could happen with specific collectors that the application freezes for seconds and nothing happens. You can't do anything. And then suddenly it continues working. And that have been this terrible stop the world garbage collection process that people sometimes talk about. So this is when we talk about stopping the world, this is what we mean. Stop all application threads and give the JVM time to do the garbage collection. Okay. But this is just the basic that if I talk about stop the world, this is what I mean. So let's take a look at the different collectors. And I don't mean the garbage collectors in the JVM. I mean the collector principles, because there are different ones. And most of you probably heard the one or the other. So we start with the so-called non-moving collector, also known as mark and sweep. And I think all of you heard of this one. And to make it easier to understand, I created little demos that shows you how the mark and sweep collector works in the heap. This is very simplified, right? So you see this is my virtual memory. That's the heap. You see these objects, which is the free cells, right? It's not object, it's free cells. But in my example, every object takes one cell to make it as simple as possible. The gray ones that you see here, this is free memory, unused. As soon as it's blue, it's used memory. So that means it's live. There's a reference from the stack to the heap. It's reachable, okay? If it's purple, then it means it's dereferenced. That means it's dead. There's no reference anymore, so it's a dead object. Then this is purple. If it's blue and has a red square on the upper left corner, that means the garbage collector traced it and marked it as live, right? Remember, there have been tracing, freeing, compaction. In this collector, we have tracing and freeing. So that means At one point, we stop the world. The garbage collector starts marking all the live objects on the heap. And then this is this little red square that you see. After it marked the live objects, it will remove all the dead objects. And then it will continue running. If you see a number in an object, in a memory cell here in this case, that means this object or this memory cell survived one garbage collection cycle. So that means we fill up the heap, we stop the world, we do the garbage collection, we continue running. All the objects that are still alive, they get an increase by 1, and that happens every time. In this collector, it's not needed, but in other collectors, you will see the effect of that. So let's take a look how it looks like. So we start, you see, we start collecting, objects will be allocated and will die very quickly in this example. So all the purple ones are dead, the blue ones are alive. Once we fill up the heap, at one point we have to stop the world, mark, remove the dead ones, continue. You see now, mark, remove, continue. And this is how the mark and sweep collector works. You see already the problem that we have, probably after some time. See, oh, okay, stop again, free. Very simple principle, and it works. So the problem that we have with this collector is that if you're old enough, you remember Windows 3.11, and you have to defragment the hard drive, because this is exactly what happens on the hard drive too. So you fill up space continuously, and then you remove stuff. And then you have all these spaces in between, as you can see here. That means we increase the fragmentation of the heap in this case. And it gets harder and harder to find free space, especially if you need big objects, right? So in this case, it's simple because each cell is one object, but you can imagine if you have large objects, you have to find, if possible, a continuous space, which makes things harder. Okay, that means problem is fragmentation, and that leads me to the next collector types, right? So we have the so-called moving collectors, because in this collector, we saw nothing moved. We allocated memory, we marked it, the live ones, and we removed the dead ones. And then we filled the empty spaces again and again. So there's nothing really moving, right? So that's the reason why it's the mark and sweep is a non-moving collector. And freeing, just to make that clear, means we have to go through all the cells and check, is the cell free? Okay. Is it live? Okay. Is it dead? Remove it. And we have to do this with all the cells. We have to go through the whole heap. And you can imagine the larger the heap, the longer it takes to free memory. Okay, but let's move on to moving collectors. And we will start with the so-called compacting collector, which is mark and compact. And mark and compact is very similar to mark and sweep. We have one additional step. As you can see on the left, first of all, we allocate memory, objects will die. Once we reach a specific amount of memory filled up, and in this case, we need a little bit of headroom, because if we start moving stuff around, we need some spare space where we can copy stuff first and then free some stuff, move it around. So, right, so that's something you will see. We won't fill it up completely here. So once it's filled up to the limit, we mark the live cells, we remove the dead ones, and then we compact everything to the upper left corner in this example. But let's take a look, because then you get a better impression how it works. So again, we allocate memory, objects will die. Once we fill up, I think it's the last row or the last column will be free in this case, and then we stop the world. So that will be now, okay. Mark, now compact, see? And then we start from scratch. We have free room ahead of us. So that means we can allocate fast. We don't have to look for free spaces. So in this case, and again, mark, remove, compact, and you go again. This is how mark and compact works. And that's already better, right? Because we always have free space ahead, so we can allocate fast, which is good. But the compaction, of course, needs more time, right? So it's an additional step that we have to do every time. Okay, so that means the drawbacks is we need some more headroom, depending on how large the heap is, to be able to copy stuff first to the empty space and then back to the upper left corner in this case. So the compaction needs a little bit more headroom here. That leads me to the next one, which is the so-called copy collector, which is also a moving collector. And you will see that this one is totally different. Instead of having just one area, we have suddenly two, and they are called to space and from space, and they will toggle. So you will see once one space is filled up, they will switch names. That means the to space becomes the from space, and the from space becomes the to space. And the big advantage of this one is, as you will see in the demo, once it fills up, we mark all the live objects, and then we copy the live objects to the near now to space, right? And then we know that everything that is in the left side in this case is garbage. We don't have to check every cell anymore, right? Is it free? Is it used? Before we free it, we can just free it directly, right? This is the advantage of having the copy collector. And so let's see how this works, right? It's in principle the same. We fill up the orange space here. Once it's filled up, you will see it will toggle orange and gray. So the to space will become the from space. We mark all the live objects, copy them to the now to space. Now you will see it will happen. Mark, copy. Now we can clean up completely. We don't have to check if there's anything still alive because everything that's live we moved. But moving stuff around in memory always means we have to update the references, right? Remember, from the thread, the stack frames, the references that point to the objects, when we move objects around, we have to update these references, right? This is the drawback of copying stuff, right? But we win that we don't have to go through each cell and check for freeing it. And you see this is going back and forth, and which is a quite interesting approach, but you already see the problem that we have here. First of all, if we have objects that really live for a long time, we have to copy them every time, right? Even if they live for the whole application lifecycle, we have to copy them, which is one thing. And the other thing is we need more or less twice the amount of memory, right? This is the other drawback that we have with the copy collector. If you have a large heap, like 10 gigabytes, then you need 10 gigabytes again for the other place to be able to copy stuff around. Okay. That leads me to the generational collector, which is, in this case, generational mark and compact. And you will now see this is not a completely new one as we saw before. This is now a combination, right? And before I start with that, I have to talk about the weak generational hypothesis, which means objects die young. And this is not only for Java. This is for objects in general, for all kinds of languages. Scientists figured out that if we have this chart here where we have on the y-axis, we have the number of objects, where we have on the x-axis the lifetime of objects, then this is the chart that you probably saw already somewhere. So that means we have lots of short-living objects. So we allocate and they will directly die. Then we have a couple of objects that have a medium living span. And then we have lots of objects that just really living, a few objects that's just living for a long time, right? You see the number of objects is the most where we allocate and then they will die directly. Then we have a couple of medium living and very few long living objects. So if we take for the creation of objects, right, where they die young, we take a space and we name it Eden space. This is how we name it. And in this space doesn't have to be very big because you see it's not really, it's not a huge number that survive there. And they will just allocate it and will die. And if it's smaller, then garbage collection is faster. And then for the medium living objects, we take a so-called survivor spaces. And you see already, this is a copy collector. And there's a reason for that. And we will come to this. And then for the long living objects, we take so-called tenor space, right? So there we store all the long living objects. So when we talk about Eden and survivor, so the left part of this chart here, then this is the so-called young generation, right? And then the right part, the tenor space, this is the old generation, objects that really live for a long time. And if we talk about collections, then doing a collection in the young generation, this is a minor collection. Doing a collection in the tenor space or in the old generation, this is a major collection. And if we do both, then this is a so-called full collection, right? And the principles can be different. So for example, for the tenor space, we could use something like mark and compact, right? Only for this space, where we can use another principle for the left one. We see the copy collector already. We could use a mark and sweep for the Eden space, for example. Okay, but I created a demo again so that you get an idea how it works. And now you will see that objects that survive 3 garbage collection cycles will be so-called promoted from the survivor spaces to the old generation, to the to-nerd space. You will see that. And that's the reason why we have the numbers in the objects here. So let's take a look at it. So we start allocating objects will die young. We just copy the live ones to the survivor space, to the to space, remove everything in Eden, and continue collecting. And in between, objects will die also in the survivor spaces, right? So you see how that works. Once objects survive 3 times in the survivor space, in the garbage collection cycle, they will move over to the to-nerd space. They will be promoted. And then you will see, I will do a fast forward. It will fill up like a wavefront. It will move through the Eden, through the old generation, as you can see, because even their objects will die. Until it's nearly full, we do a full collection here. So we stop, we mark, and compact, right? You will see that in a second. On the to-nerd space, the right side, because nothing fits in anymore. So we have to do something. We mark, we compact, and then we copy everything from the young generation into the old generation. And then we can start from scratch in the young one. This is mark and compact, a generational one. And now we can continue, right? So this is the whole principle, how it works. The big advantage that we have with this one is we can always allocate fast because the Eden space is relatively small because objects will die young. Garbage collection in Eden is very quick. The copy collector in the survivor spaces will take care about long-living objects so that we don't have to copy them all the time. After 3 cycles, in this case, they will be promoted to the to-nerd space, where they can stay for a long time, right? The reason why the to-nerd space is so big is that because this is mark and compact, that means we have to go through all the cells and check if they are free, if they are used or not, to free them. And that takes time. The bigger the to-nerd space, the longer it takes until we have to do the full collection or the Mayer collection when we just talk about the old generation in this case. Okay, that was this one. The question is, you saw we have young generation, old generation. We have references. They're going from the stack frames into these generations. What is about references that pointing from the old generation back into the young generation, right? Because if we do then a collection, right, in this case, we have the young generation on the left side, we have the old generation on the right side. We have the stack frames on top here, the roots. So we do a minor garbage collection. That means only in the young generation. And these are our stack frame references to these objects. Now you see in the minor GC, there are 4 blue cells. Only 3 are marked because the minor GC only takes care about young generation. So there is this reference coming from the old generation, pointing into the young one. So that means this is a reachable cell, it is used, but the garbage collector doesn't find it because there's no reference coming from the roots directly to this cell. And he's only doing the garbage collection in the young generation, so he has no idea about the old generation. How does he find it? How is this reference found? Well, there's a so-called card table. This is also known as the remembered set. So the JVM takes care about especially these references and puts them in this so-called card table. And the garbage collector can look up the card table, find the reference, mark it as live. And so the JVM can take care about that. Even if it's only doing a minor GC, it will find the references coming from the old generation. And vice versa, it's the same. Right? So this is just if you stumble upon that. So you don't have to understand all of this. It's more like you will stumble upon these words like card table, remembered set. Just keep in mind, this is for intergenerational references for the garbage collector to take care about it, right? This is the whole thing. That's all easy, right? This is just simplest or most simplified version of serial GC stuff. That means we'd stop the world. What about concurrent collection? So if we would like to do that during the application when the application is running, at the same time we will do a garbage collection. How to do that? Well, concurrency is hard. And if we look at stop the world, this is not available anymore here. Concurrent means we don't stop the world. We have application threads and we have garbage collection threads at the same time, working on the same memory. that has some implications, and I will show you some of them. So for example, if we mark things, right? If we follow all the references that coming from the stack frame and mark them in memory and see this is a live cell, this is a live cell, and so on. How do we do that concurrently? That means when the garbage collector starts finding these things, in the meantime, the application threads can allocate more or even remove references, right? Or objects can die. So somehow we have to find a way to take care about that. This is about concurrent marking. This is only marking live cells. And you see the square on the left side, which is the root, it's the stack frame. We have a reference that points into the heap, and we have the first reachable object here, right? The garbage collector will mark stuff. He said, oh, this is reachable. This is the gray color. And then it goes on and say, yeah, it's live. I go to the next one, to follow the reference tree. So it marks this one as reachable. And then suddenly the application thread decides, you know what, this reference that's going back to this first object there, I just remove it. The garbage collector doesn't find it anymore, right? So it just continues. And then the application thread decides, oh, I establish a new reference here from this object. Garbage collector already passed the object and marked it as live. So he will just continue following the references until everything is marked, and he will miss the first one. He won't find it. And this is a no-go, right? So you can't do that. So we have to find a way to do that. And the answer to that question, how can we do that, is we use barriers, right? And there are so-called write barriers and read barriers. But the principle is more or less the same. So what it is it's a mechanism to execute code before either an object is read or written to a memory cell. This is the idea, right? So you have to install it on each memory cell, more or less, right? And every time the application thread is reading this cell or writing to it, it has to execute this code. So you might think already, okay, there's a lot of reading and writing going on, so the code has to be very efficient, right? Because otherwise you have to execute all this code all the time. It will bring down the performance completely. So it's used to keep track of intergenerational references like the remembered set, as we saw on the card table. This is also can be done via barriers. And it's also used to synchronize between the allocator and the collector, right? So you can use these things. One thing you have to keep in mind is that read barriers, usually we have around 75% of all the memory access is reading and 25 is writing. So that means if you install a read barrier, this has to be very efficient because it will be triggered way more often than the write barrier, okay? So this is something you have to keep in mind. Okay, so same idea now, and now we use write barriers. So what it is on each of these memory cells is a write barrier installed. The collector starts marking the cells. It follows the references. It finds the first one. This is reachable. Okay, it goes to the next one. First one will be marked as live. Now the allocator removes the reference, but it triggers the write barrier here. And the write barrier in this example says, if you remove a reference, the former cell that was referenced should be marked as reachable. This is the code, right? So it will mark this one as reachable by the code that is in the write barrier. The collector doesn't know. It just continues like before. The difference now is once it finished with all the marking, you see there is now this gray reachable cell. And to find that one, there is a so-called remarking phase, right? So the collector goes through the memory first, and everything that changed in between before he finished is marked. So then he has to do a second run. And this is then, it's like a stop the world, but it's very short. And now in this remarking phase, it will find this reference, will mark it as live. And so this is how you can do it using a write barrier. There are other principles, but in this case, this is the way how you could do it. This is also known as snapshot at the beginning. If you stumble upon this sentence, then this is what they mean. If we talk about concurrent copying, that's a different story, right? Just imagine you have the heap, you have objects lying around. Now you do a compaction. You copy an object from one space to another space, and you have to update the reference. And at the same time, The application is running, right? So that's if we stop the world, then this is what it looks like. So we have the object on the heap with its header, and we have the references pointing to this header. It's all good. So we stop the world. No application thread is doing anything. Then we copy the object to the new location. Then in the header, the forwarding field, we just install the forwarding information, and then we update all the references so that they can point to the new location. Once all references are updated, we just continue running the application, easy peasy, right? This is if we stop the world. So if we don't stop the world, then this is what happens. We take the object, we copy it to the new location, and we start updating references. But the application threads still accessing this memory. Now suddenly, both of these objects are reachable, right? So that means, and they can be accessed by the application. So threads can access either the one or the other. So which is the right object? That's the big problem here, right? So you can't just simply copy stuff and update references while the application is running, because this kind of stuff can happen. So one thread can write in one object, the other can write in the other one. So that we have to find a solution to fix this problem. Well, because the problem is which copy is correct in this case. There's one solution which is called so-called Brooks pointer, and that's because the guy who invented that is what was called Brooks. And we install a forwarding header in front of the object header, right? And this forwarding header points to the header itself. That's the idea. All the references point to this object forwarding header. It's all good. Now we copy the object to a new address. And before we start updating references, we install the forwarding header, and that's pointed to the right header, right? So that means in this situation, the right object is not visible to anything because no references have been updated yet and no one can see it. So now if we start, before we start updating the references, we now point the original forwarding header also to the second object. And this is an atomical operation, right? That means this happens without having accessed from the application threads. Now, if we now update references, it doesn't matter if application threads will access this, because even the ones that access the old object will now find the path to the new one. Right? This is how you can do it using a Brooks pointer. And then when everything is updated, then you can remove the original object, right? So this is a way to do concurrent copying using the Brooks pointer, right? So without really breaking the system. Again, you don't have to remember all these things. Important is that you get the idea what you can do by using a so-called Brooks pointer, right? Okay, now these are the principles, very basic explanation. If we take a look at the collectors that we have in the JVM, then we have different ones. And we start with the simplest one, which is the serial collector. And the serial collector, as the name implicates already, it is, you have lots of application threads running. And then you send the signal, and then the save point signal, then everything stops. And then you have one thread that does the garbage collection. Once this thread is done, we continue with all the application threads, okay? That means if there's a lot of garbage, it takes some time, right? But this is just, but it's very simple. It's very simple, and it's also a very good collector for specific use cases. As you can see, if you have a single core system, one CPU, one core, with a small heap, then this is quite okay. If you don't have any pause time requirements, right? So if you say, I don't care if the application or the service stops for a second or two, it's not really important to me, then this could be a quite good collector, right? It's best suited for single-threaded applications, development environments, microservices on small nodes, right? And this leads me to the next thing, because this collector will be automatically selected if you don't specify a garbage collector. And you have, for example, you have a node in your cluster defined, and this node has less than 1.8 gigabytes of RAM, or it just has one CPU, the JVM will automatically choose serial garbage collector for you. So you don't get G1, you get serial, just to keep that in mind, right? So if you specify, you can change stuff, but if you don't do it, if you just use the default, then the default will change to serial collector if the memory is less than 108 gigabytes, or if you just have one CPU or one core. Okay? And you see the young generation algorithm is a copy collector. You know what that was, right? And then we have mark, sweep, and compact for the old generation. This is how the serial collector works. It's not a bad collector. Like I said, for specific use cases, quite useful collector. Leads me to the next one, which is the parallel one. The difference to the serial collector, and again, the name says it already, we have lots of application threads. We send the JVM save point signal, all the threads stop, and now we use all available threads for garbage collection. Serial just used one. We use all available, and then we continue. And this is the reason why this collector is also called the throughput collector. Throughput, when we talk about JVM and garbage collection, is the time you spend in garbage collection versus the time you spend in the application. If you have all threads available for garbage collection, you can imagine garbage collection can be really fast, and that means short. And this is why this is the collector that has the highest throughput from the standard collectors that we see in the JVM. You can choose it if you have multi-core systems with smaller heaps, so less than 4 gigabytes. If you need peak performance, because like I said, the throughput is very high, without pause time requirements, you will have pause times with this collector, and they are not predictable, right? So you can't really say, oh, I would like to have now the garbage collection. This is not possible, as we know. But that makes it very good garbage collector for batch processing, for example, or scientific computing or stuff like that, where you really need throughput. And you always see here where it's available, the operating systems, the JVM switch in the bottom here, how to switch it on. You see it's parallel, it's not concurrent, it is generational. All the collectors in the JVM are generational except one, and we will come to that in a second. You see the CPU overhead is quite moderate, it's not really high. The reason for that is these are collectors that are not concurrent. If you have concurrent collectors, that means if you have 10 threads available in your JVM, for example, and you have this kind of collector, then you can use 10 threads for your application. Then you have stop the world, 10 threads for garbage collection, continue, again, 10 threads for the application. If you have a concurrent collector, then it means you might have 9 threads available for the application because one is always doing garbage collection. So it's always, if you do a concurrent garbage collection, you don't have the same amount of threads available for that, right? Because you need threads to do garbage collection at the same time. That's the reason why it always brings down a little bit performance if you use a concurrent garbage collector. Just keep that in mind. All right, that was the default garbage collector in JDK 5 up to JDK 7. Again, copy collector for young generation, mark, sweep, and compact for the old generation. Next one is CMS, concurrent, mark, and sweep. In principle, this one looks very similar to the one that I showed you, the generational mark and compact, very similar from the structure here. And you see already it's deprecated. So this is not available in today's JDKs anymore because it died with JDK 13. It was already deprecated in JDK 9, and then in JDK 14, it was removed. So if you are on JDK 17, 21, whatever is after 14, or after 13 in this case, you won't have it. You can't even switch it on. If you try to switch it on with use conc mark sweep GC, you will get an exception. It won't start. That was the idea behind this collector, was to have a collector that has predictable response, predictable short times. That means not longer than a second. That makes it quite predictable, right? And if the response time is more important than the throughput, this was a quite good collector. It was good for web application, medium-sized enterprise systems, but most of the users don't use it anymore because it's not available these days, right? And it has a successor. So it was, like I said, deprecated as of JDK 9, removed from JDK 14 onwards. You see it was partly concurrent because it does concurrent mark and sweep for the old generation. And if you do full GC, it's mark, sweep, compact. We saw what that was, right? It is marking, then you free it, then you compact everything. And this is if you do full GC. And this is the successor of CMS, which is garbage first. And this is today's default collector at the moment. And this is a completely different one. As you can see, we don't have these big regions anymore. Now we have small regions, right? Let's say we don't have big areas. Now we have regions, because this is a so-called region-based collector. And you see on the left side, the region size varies depending on your heap size. If you have a heap size that is bigger than 64 gigabytes, you get 32 megabytes for each of these regions, right? If it's smaller than 4 gigabyte, it's 1 megabyte for each of these regions. And there is an example calculation below that. You see, this is how it looks like if nothing is assigned. If we now take a look at it, how it looks like if there's something assigned, then we see Eden regions, remember, where we create new objects, right? Where they die very quickly in these regions. Then we have survivor region, which is the orange one. And then we have inert regions, which are the blue ones. There's also a so-called humongous region. A humongous region is if you have an object that is bigger than half of one region size, you will get it directly as a humongous region. That means it's more or less directly to inert space. It won't be copied around and stuff to avoid copying objects. That's the idea behind it. And of course, I have a demo. And you can see how this works. In this case, I have 6 Eden regions. So you will see 6 yellow regions filling up slowly in the beginning. And once they are filled up, I take the 2 regions with the most garbage in it. And then I do from this one, I copy the live objects into a survivor region, which is garbage first, right? Because if you have a lot of garbage, then you just have to copy a few live objects, which is fast. This is, you see, it's very optimized. And the small region size makes it even faster because you don't have these huge areas that you have to clean up or mark or stuff. You just have these small regions, which makes the whole thing faster. But let's take a look at it. So we start collecting stuff or allocating stuff. And you see, remember we have 6, and you will see, you see objects die already in the Eden space. And once the 6 are filled up, we take the 2 with the most garbage and copy the live ones. You see, we have 2 survivors regions in this case here, and we continue with this. And then once the survivor regions, and we have 3 filled up, then we have to promote stuff in inert regions, right? Yeah, you see, we have 1 inert region here. And then we continue. And you can already see this is quite flexible because there's always 3 regions and you can just pick them. And once you're done with one region, you can just wipe them out because everything was copied out, right? The live objects have been copied out of the regions into another region, and the rest is just garbage. You can remove it because it's small, it's fast. And of course, the number of Eden regions, survivor regions, and all this is all, you can define all these kind of things. How many regions you need for the inert space and all that kind of stuff. But you get the idea how that works. This is in the JVM, that was the first collector that works with this new principle with regions. And from this moment on, all the collectors that we have today, the newer ones, all are region-based. So it's a different approach to garbage collection, but a more successful, or let's say a more faster way to do it. Because of the smaller regions, makes it easier to even allocate bigger amounts of memory and handle bigger amounts of memory in a specific or defined time frame. Okay. Yeah, you can see it goes on and on. So we see even the inert space will die and so on and so on. Okay, so this is the G1, how it works. In principle, as I said, this is just a demo, right? This is not really how it works. This is that you can have an idea how it works. Again, this is the same as for CMS. If the response time is more important than the throughput, very good collector, right? If the pause time must be kept shorter than 1 second, very good one. That's the reason why this is the default garbage collector in the JVM in OpenJDK, I have to say. If we talk about OpenJ9 or Samaru from IBM, which is another implementation of the JVM spec, they have different garbage collectors, probably work very similar, but they are completely different, right? So this is only for OpenJDK-based JVMs. As I said, this is the default collector right now. And I always ask people when I do this session in conferences, who is actively changing or setting the garbage collector in his application. And most of the people say, no, I don't. That means this collector works quite good out of the box for most of the use cases, right? So this is the reason why it's a good default collector. As I said, it's default from JDK 9 onwards. It started with JDK 8, but in JDK 8, you have to switch it on manually. It was not the default. We have a so-called evacuating collector for the young generation, which is mark and compact. Then again, this is also partly concurrent marking and compacting, and mark and compact for full GC. And that leads me to one of my favorites, which is Epsilon. The Epsilon collector, which is a no collector collector. That's what I name it. And as you can see, it's a garbage collector that is no garbage collector. It doesn't do any garbage collection. That sounds funny. The reason is, if you would, for example, you have your application and you do some performance tests. And if you just do it with a standard JVM, when you do the test, there's always garbage collection involved. You also measure garbage collection, right? So that means you have to do a couple of tests and then take some medians and stuff to get the real value, because you have garbage collection. They are not predictable in between. If you would like to measure application performance only, then you could run your application without doing garbage collection at all, if you know how much memory your application needs. And that's the hard part, right? I didn't tell you from the beginning, because you don't want to really run that on a monolith, right? Because this can be huge and you have no idea how much memory it needs. But if you have microservices, and if they are small, then you probably might know this service never allocated more than, let's say, 2 gigabytes. So you can set the max heap to 3 gigabytes, and then you will run your application without doing any garbage collection. And that's the big advantage, because you can already see, if you need to test performance or memory pressure, very good collector. If you need the highest performance, right, then you can use this. But keep in mind, there is no garbage collection. You will run out of memory if you don't know exactly how much memory your application needs, right? So this makes the use case very specific. As you can see, for extremely short-lived jobs, it's nice. If you need the last drop latency improvements or last drop throughput improvements, this is a collector you can think about. You can at least play around with it, but you will figure out, if you just use it without knowing what you're doing, you will run into out-of-memory exceptions very quickly. It's only in OpenJDK. As far as I know, IBM OpenJ9 doesn't have this kind of collector, and I think it started with JDK 11. Leads me to the next one, Shan Andor. Shan Andor, quite interesting collector developed by Red Hat. Roman Kenke was one of the main developers here. He left Red Hat in the meantime, is now at Amazon. And this is the only non-generational collector in OpenJDK. This is also a region-based collector. It's made for, if you need a very short breaks, or the response time is very high. If you have very large heaps, like 100 gigabyte plus or whatever, can be even more, and predictable pause times. I think they guarantee something, I'm not quite sure, but I think it's 10 milliseconds as far as I know. I might be wrong here, but this is the range what we are talking about. So very fast collector, very short pause times. One thing you have to keep in mind, even all the concurrent collectors that we have do very, very, very short stop the world pauses. They are so short, like I said, 10 milliseconds. They probably, you won't even be aware that there was a pause, right? That's why we say they are concurrent. There are no, don't stop the world, right? But they do, in reality, they do. But it's very short pauses. So this is best suited for latency-sensitive applications, large-scale systems, highly concurrent applications. This collector is not available in Oracle JDK. It is available in all builds of OpenJDK. Oracle JDK is also a build of OpenJDK, but they don't have it in there. Don't ask me why. Maybe they don't invented it and so they don't support it. I don't know. But it's not in Oracle JDK. You have a little bit reduced throughput because it's a concurrent GC, right? Fully concurrent. And that means we have threads that are not available for the application because they're doing garbage collection. And they make use of a new barrier concept. So they use load reference barriers, which is read barriers here, very efficient ones. Leads me to the next one, ZGC. And the name is wrong. It's not zero garbage collector. This is, I thought it was the name, but it's not, so I have to remove it. I think it's just the Z garbage collector. which is the newest one in OpenJDK. And again, it's a region-based collector, more simplified. We just have young generation, old generation. There's nothing like survivor spaces in this case. If objects live longer, they will be promoted into old generation. That's how it works. And so this is in principle the heap layout here. I won't talk a lot about this collector because there's one more, and this one is, it looks like a more or less copy of the next one. So that's the reason why I will explain the next one in more detail. So this is a fully parallel, fully concurrent collector. It's fast. It's made for huge heaps, could be terabytes. Very short pause times, could be around 3 milliseconds. So again, if you have low latency sensitive applications, large scale systems, highly concurrent applications, this is your collector, right? At the moment, oh, not anymore. Before JDK 23, it was non-generational, right? And now we have a generational version. Since JDK 23, ZGC is generational in OpenJDK, and the non-generational version is already deprecated. So it will be removed in the future at some point. The reason is the generational one is just faster, so why keeping the older one? Okay, you see the CPU overhead is a little bit higher here, right? Because this collector, especially if it handles large heaps, needs more CPU to do concurrent garbage collection, which takes away threads for the application. It will probably become the default garbage collector in the future. And as I said, the non-generational version is already deprecated. That leads me to the last one that I have, which is the C4, Concurrent Continuous Compacting Collector, which was invented or created by Azul a long time ago already, more than 10 years. And this is only part of Azul Zing, which is a high performance JVM. And we use the so-called loaded value barrier everywhere, which is a read barrier, very fast one. We just need one CPU cycle. Remember, I already told you a read barrier has to be very fast because it will be executed every time when you read a memory cell. And we can do that in one CPU cycle, which is fast enough, right? And it makes sense to use transparent huge pages if it's only available on Linux. And on Linux, you can define the memory pages size. There's the THP, and it makes sense to use them to get more performance. And I will just tell you about the marking phase, because this is, like I said, this is the same as in ZGC. ZGC copied all these principles. They name it differently. They don't say loaded value barrier. For them, it's colored pointers, but it's the same, right? The non-generational version was a one-to-one copy of C4 non-generational. The generational ZGC is a little bit different because they also make use of a write barrier, where we only use read barriers. Marking phase in this case is a little bit different than we saw before. This is concurrent marking. You see the orange gears here, which are the GC threads, the garbage collection threads. They start with the roots, following the references, and marking live objects. And they always trigger the loaded value barrier, which is this one CPU cycle code that will be executed. So if we now go on and we mark all the objects live and we reach this place, then suddenly the application thread steps in and just allocates memory. And now it hits the loaded value barrier and it triggers it. The code will be executed. And these codes lead to the fact that the application thread through the loaded value barrier will mark the cell, right? It will do a test and jump. This is the instruction that we do. And then it will mark the cell as live. And it will pass this information to the garbage collection thread. And so the garbage collector doesn't have to do the remarking phase, right? That we saw before. Remember, there was this, the garbage collector goes there, then we have this write barrier, then we have the remarking phase. We don't have to do that because in this case, the loaded value barrier will mark, or colored pointer in ZGC will automatically mark even when the application thread accesses a memory cell, which is a big difference, right? So that means the GC doesn't have to do it again. It directly knows, even if the application threads accesses new memory, allocates new memory, it will mark it as live, which is quite a big benefit here. So no need to mark again by the GC. And another thing that is interesting, which is called quick release, if we have objects that lying around in these different regions, right? In this case, we have the Eden regions here. Now we do a compaction, so we move everything into a new area, instead of storing, remember we had this, when we copied stuff concurrently, we have the header of the object, and then we have a forwarding pointer that we install in front of the header. Instead of installing it in front of the former object, we just take the information, ZGC exactly the same, and we save it in an off-heap page, right? So that means in the off-heap page, we see, A is now A plus or whatever, and B is B plus, C, C plus. So the information where to find the new object is in the off-heap page and not in the original object anymore. So that means once we moved everything, we can directly, because this is virtual memory, and below the virtual memory at some point, all this stuff is stored in physical memory, right? But physical memory, we have to free it as fast as possible to make it available for new virtual memory. I know it's complicated. So that means this is the physical memory below it. As soon as we moved everything to the new place, we can just clean up all the physical memory directly. And the reason is we have the forwarding information in the off-heap page. It's not in the original objects anymore. If you use the other approach with the Brooks pointer, for example, you have to keep the information until you have updated all the references, then you can remove the physical memory because you still have to access it. In this case, we don't have to, and also ZGC doesn't have to. Okay, that was a quick release. Shortly, it's only available in Azul Zing. We can handle also up to 20 terabytes of heap without doing really garbage collection pauses. Like I said, there are pauses, but they are so small that you can't really identify them. Not in the application. Of course, you can measure this stuff, but it's really small. It's below 3 milliseconds. It's for low latency sensitive applications, large scale systems, highly concurrent applications. It's only available in Linux. The reason is that we fixed some problem in the Linux kernel to make the memory access, and this is not a joke. We measured that and we have a proof. It's 1 million times faster using our approach than the Linux kernel approach, which is the reason why it's only available in Linux. But that makes memory access way faster. One advantage that we have that is not in OpenJDK is in our Zing JVM, we also have our own compiler, which is faster. It produces faster code. That means we don't have this big, well, it's not really big. Let's say we don't have the drawback of performance lost because the compiler produces faster code. We don't need that many amount of threads to run with the same performance, which is a little bit of a benefit here. All right, now I showed you all the different garbage collectors that are available in OpenJDK and derivatives of that. The question is which one to choose, and that's the hard part. Lucky us, there are only 3 essential criteria that are really important to know, which is throughput, right, latency, and resource usage. That means throughput, I told you, time spent in garbage collection versus time spent in an application. Latency is the responsiveness of the application. Resource usage is how much memory does it use, how much CPU will it drain, and stuff like that. So, lucky us, you can only choose 2 out of 3. Well, makes things easier, right? So it means either you have very high throughput and very low latency, but then the resource usage is high. If you say, I need low resource usage, but I need very low latency, you won't get high throughput. This is how it works. To make it easier for you, this diagram gives you an idea where if you have pause times that should be very small, like 1 millisecond, then you have to go C4, ZGC, Shan Andor. If you say, then I have runtime overhead. If runtime overhead is more important, then you go to the right side. It's serial and parallel. Like I said, most of the people are in the middle, which is G1. CMS is deprecated. That's the reason why most of the people are good with the default garbage collector. If you work, for example, with high-speed trading applications, then you go to the left side of the diagram. If you work with batch processing or stuff, then on the right side, it's better for you. Or if you have very small nodes in your cluster, for example, then the right side is the better one. Because G1, for example, isn't very efficient with very small heaps. So then you can better use parallel or serial for that kind of stuff. To give you an overview, because this is recorded and you can probably take a look later on, I created a table where you see all the different things in one table. It's quite complex, so I won't go through any details here, but in principle, it contains all the information that you need. The availability, is it parallel, concurrent, generational, heap size, pause times, throughput latency, performance, CPU overhead, and tail latency. So you can get an idea if you take a look at this one. If you want to know more, this is the book. It's the holy grail of garbage collection. Be aware it's complicated, but if you would really like to know more about it, this is a really nice book. The third, I think it's the third edition, the current one, which is quite good. The older ones didn't cover all of that, but this is a really good book if you're interested in garbage collection principles. Be aware this is not based on Java. This is mainly C++ when they explain it. With this, I'm done. Thanks for attending. And if you would like to know more about no fluff just stuff, then check out this QR code or go to the website. They have lots of webinars and conferences coming up. So that's it with this session. Thanks for attending.